In the chapter Normal Modes of Continuous System, we have started to deal with the problem of longitudinal vibrations of a rod. Actually, in this lecture, our aim is to find the normal modes for the longitudinal vibration of a rod. And actually, in the first part of the lecture on this subject, you have seen how we can obtain the equation of motion of the particles of the rod. Okay? So you can remember, I have considered that this PQ is a solid rod lying along x-axis. And when no disturbing force or external force is exerted on this rod, then the particles of this rod is in equilibrium state or equilibrium position. Actually, for calculation, I have considered that there is a small element of this rod marked by this AB, and these dots actually represent the different particles which constitute this element. And relative to an arbitrary origin, we consider that this x1 is the x coordinate of section A and this x2 is the x coordinate of section B. So the length of this element which we have considered is actually delta x, which will be equal to x2 minus x1. Okay? This is the situation when the rod is in equilibrium state. That is, no perturbing force, no disturbing force, no external force has been applied on this rod to vibrate it. But now let us consider, we exert a force, let us say F, along the length of this rod. So when this force will be exerted, let us say by a hammer, then the particles of this rod start vibrating on the line of the action of the force. And so it is actually called longitudinal vibration. Okay? And I have shown in this figure that this section A is displaced to A dashed and B is displaced to B dashed. Okay? Actually, considering these ideas, you have obtained in the first part of the lecture the well-known equation of motion of this vibration. And after getting the equation of motion, we have actually obtained a very important equation which I have mentioned here. This is del 2y by del t square equal to v square times del 2y by del x square. Here actually, you know, this y of xt, this is actually the displacement of a particle of this rod at any moment t situated at point x equal to x. Okay? And we have obtained in the first part of this lecture that this v is equal to a square root of y over rho, where you know y is what? This is Young's modulus of elasticity of the material of the rod, and rho is its density. Okay? So this was the final result which I have mentioned here, but how this result comes, we have already learned in the first part of the lecture on longitudinal vibration of a rod. Okay? So actually in that lecture, we have obtained the equation of motion of the particles of the rod. Okay? But now we are going to find the possible normal modes of longitudinal vibrations of the rod under the given boundary conditions, which we will impose a little later. You will see what boundary conditions we will impose to discuss its normal modes of vibration. And for this, let us consider that there exists a normal mode at a frequency, let us say omega, and phase constant phi. Okay. When you say that there exists a normal mode at angular frequency omega and phase constant phi, what does it mean? Actually, it means that in that mode, every particle of the rod executes simple harmonic motion of angular frequency omega and phase constant phi. Okay. So the motion or the vibration of the particles of this rod can be represented by this equation, which is actually the solution of the differential equation of SHM. Y of xt is equal to A of x times cosine of omega t plus phi. Where you know, what is this y of xt? Actually, y of xt, you know, is the displacement of the particles of the rod. Since y depends both on position and time, at the same time, displacement of particles at different position will be different. Okay? And at the same position, displacement of the particle at different time will be different. That's why y is a function of the space coordinate x along with the time coordinate t. Okay? And now, since y is not only a function of t but also a function of x, so actually in this case the amplitude of SHM is also position dependent. So I have written A of x. Actually in the argument of A I have written x, which indicates the x dependence of this amplitude. Okay? And you know, omega is the angular frequency and phi is the phase constant or initial phase. Actually now from this equation, our aim is to find what will be the values of this second order partial derivative of y with respect to t, and also the second order partial derivative of y with respect to x. And finding these two partial derivatives, we will substitute those values in this equation of motion A, and then you can obtain the normal modes of frequency. So let us try to find this. And for this, let us differentiate this y with respect to x partially. But you know that A is only a function of x. So here I have written del A by del x, but that will be simply equal to dA by dx, because A is only a function of x. So there will be no difference between the partial derivative and the ordinary derivative of A with respect to x. But for a time being, I have written the partial derivative of A too. So del y by del x, you can see this will be del A by del x times this much. Here, cosine of omega t plus phi will be treated as a constant factor because we are differentiating partially with respect to x, keeping t constant. And so, the second order derivative, del 2y by del x square, this will be del 2ax by del x square times cosine of omega t plus phi. Okay. Now let us find del 2y by del t square. For this, first of all, we obtain del y by del t. In this condition, this a of x will be treated as constant, and this cosine of omega t plus phi will be differentiated. And so this is minus omega times a of x times sine of omega t plus pi. And that's why del 2y by del t square, this will be minus omega square a of x times cosine of omega t plus pi. Okay. Now after obtaining these two partial derivatives, let us substitute these two values in our result A, which this result A, you know, we have obtained in our first part of the lecture on this longitudinal vibration of rod. Okay. So let us substitute it. And you can see when you will substitute these values in equation A, your result will be minus omega square times A of x times cosine of omega t plus phi, and that will be equal to b square times del 2 ax by del x square times cosine of this much. Now you can see this cosine of omega t plus phi will cancel out as it is present both in LHS and RHS. Okay? And therefore, you can write that d2a by dx square plus omega square over v square ax equal to 0. As I have told you earlier that here, since a is only a function of x, so there is no need to write its partial derivative, because partial derivative is meaningful only when our function is a function of more than one variable. Here a is a function of only one variable x, so its partial derivative with respect to x and its ordinary derivative with respect to x will be same. So instead of del 2a by del x square, I have written d2a by dx square. Okay. Now we will write k square instead of this omega square over v square. It means you assume that omega over v is equal to k. Omega over v is equal to k. We assume that this. Actually, as you have learned earlier too, here this k is just, this k has been just written in for omega over v. Okay? And you know omega is a constant, v is also a constant if the rod is homogeneous and isotropic. So in present situation we will simply say that k is a constant. But when you will discuss the wave theory, wave traveling on this longitudinal wave traveling on this rod, then you will see that actually this k is recognized as a wave vector. This is a characteristic of the wave, or you can say it is angular wave number. Okay? But here we will not say that k is wave vector, because we are not talking about wave in present situation. We are only talking the vibration of the rod. Although this vibration will create a longitudinal wave traveling on this rod, okay, with this velocity v, but we are not talking about that. Now, you know, the equation of SHM is what? You know, the equation of SHM is d2 psi by dt square plus omega square psi equal to 0. Okay? Now compare this equation of SHM with this equation 2. You can see both of these equations are identical in form. But there is one difference. Here psi has been differentiated with respect to t, and here a has been differentiated with respect to x. But since the form of these two differential equations are same, so we can say that this equation 2 is also the equation of SHM. But except that it represents oscillation in a space rather than time t, not in time t. Here a space is oscillating, not time t. Okay? Oscillation in a space rather than time t. It means A is oscillating with x, not with time. Here psi is oscillating with time, but here A is oscillating with a space x. Okay? But since form of this equation is just identical to the differential equation of SHM, so we can use the idea how to write the solution of the equation of SHM. You know, the most general solution for equation of SHM is what? This is psi equal to A sin omega t plus B cos omega t. So in the light of that equation, you can write the most general solution of equation 2 in this form. A of x is equal to a times sine kx plus b times cos kx. Actually here, a and b are two arbitrary constants. These are in fact integration constants. Okay? And these integrations constants, are determined from the proper boundary condition. We will see later on this lecture what will be the boundary condition to evaluate these constants a and b. Okay? So using the proper boundary condition, you will be able to find the value of a and b. Okay? Now, after getting this value of a of x, which is amplitude of vibration, now you can write the expression for the displacement of the rod, general displacement, which is represented by y of xt. You have defined it in this equation 1, that this is given as a of x times cosine of omega t plus phi. But you have seen that a of x is recognized like this. So let us substitute this value of a of x in equation 1, and you will get that y of xt is equal to a times sine kx plus b cos kx times cosine of omega t plus phi. Okay? Actually, this equation 4 will be used to determine the shape of the mode of vibration. Okay? So now we shall determine what will be the frequencies of vibration, what are the shapes of normal modes in case of longitudinal vibration of the rod under the proper boundary condition. So here we are going to determine the frequencies and the shapes of normal modes. And for this we consider a proper situation, that our rod is clamped at one end. Rod is clamped at one end. Let us consider that this PQ is your metallic rod. Okay? And it is lying along x-axis. Its length is L, you have already assumed earlier. And we consider that at the end P, the origin of our coordinate situation is situated. Okay? Origin of coordinate system is at P. Okay? And the rod is along the x-axis. Okay? So if the origin is at the end P, so its coordinate will be x equal to 0. And since the length of the rod is L, so the x coordinate of the other end Q will be x equal to L. Okay? So you can say that we consider a uniform rod of length L lying along x-axis, which is rigidly fixed at its end P. Okay? But its end x equal to L or its end Q is completely free to vibrate. Okay? Now you know that this end x equal to 0 is rigidly clamped. So when this rod will be exerted a force, a longitudinal force to disturb it, can the particles located at x equal to 0 will get displaced? Answer will be no. Why? Because it is clamped, rigidly clamped. So even after the disturbance is produced in the rod, the particles at the end x equal to 0 will not get displaced. Okay? So you can simply say that since the end x equal to 0 is rigidly fixed, there can be no particle displacement at this end. And when you say there is no particle displacement at x equal to 0, mathematically you can write that y of 0 comma t is equal to 0 for all t. for all time t. It means displacement at x equal to 0 is 0 at every time. Okay? And actually this is our first boundary condition, which will be used to evaluate the unknown integration constants a and b. This is our first boundary condition. Now let us think about the second boundary condition. Since there are two unknowns a and b, so there must be at least two boundary conditions to evaluate those a and b. Now you know this rod is completely free at the end x equal to L. Okay. So the condition at x equal to L must express the fact that this end is free. Okay. This means that the particles at x equal to R are free to vibrate and are under no stress. Okay. Why? How you can say that the particles at this end Q is under no stress? Because the particles at this section Q is not pulled from the particles in the right side of the end Q, because there is no material in the right side of Q. So the particles in the left side will exert a force on it, but there are no particle in the right side of Q that will exert a force on it. But a rod or a body is under a stress only when equal and opposite forces act on the body. So since at Q there is no particle in the right side to pull it, therefore no stress will be produced at point Q. So Q point is stress free, and since it is stress free, okay, so in this condition you can write that no stress acts at x equal to L. But you have learnt earlier in my first video on this subject that how this stress is given. How this stress is given. You know, Y is stress over strain. Stress over strain. Okay? And therefore stress is Y times strain. Y times strain. But you have seen that this strain is equal to del y by del x at x equal to L. This is a strain at x equal to L. And when you will multiply it by y, you will get the stress. Okay? But at x equal to L, since no stress is acting, so this will be 0. So I have written here, you can see that y times del y by del x at x equal to L must be equal to 0. Because the quantity in LHS represents the stress at x equal to L, but that will be 0. Because there is no particle in right side to pull the section at x equal to L. Since y is the Young's modulus of the material of the rod, which is not 0, therefore this del y by del x at x equal to L, this will be equal to 0. Actually, this condition will be used as the second boundary condition. So now you have two boundary conditions. The first one says that displacement y is 0 at all time at x equal to 0. It means when x is 0, then y is 0 at all time. And the second boundary condition says that del y by del x is equal to 0 at x equal to L. Now using these two boundary conditions we can solve this problem. Now let us first of all apply the boundary condition number 1, that is first boundary condition. What is this first boundary condition? You know, this is y at 0 comma t is equal to 0 for all t. So use this condition in our resulting equation number 4. Okay. So in this equation, when you will take x is equal to 0, then this y will be equal to 0. Taking x equal to 0, y will be 0. So in LHS there will be 0. Sin kx, x is 0, sin 0 is 0. So this first term will vanish. And cos 0 will be 1. So there will be only b times this much. So I have written it here. You can see that after the application of first boundary condition on equation 4, our result becomes 0 equal to a sin 0 plus b cos 0 times cosine of omega t plus pi. Okay. It means 0 is equal to b times cosine of omega t plus pi, because sin 0 is 0 and cos 0 is 1. But cos omega t plus pi, can it be 0 at all time t? Answer will be no. At a certain moment, it is possible for a particular value of time t, it is possible that this cosine function will be 0. But you can't say that at all time t, this cosine function will be 0. So definitely this b will be equal to 0. So after the use of first boundary condition, we get a very important information that this constant b is equal to 0. So if b is equal to 0, then the displacement of the particles of the rod will be what? Let us put b equal to 0 in this equation 4, which defines the displacement of the particles of the rod located at position x at time t. Since you have obtained that this b is 0, so your result for y of xt will be equal to what? This will be a times sin kx times cosine of omega t plus pi. This is actually the resulting equation for the displacement of the particles of the rod. But see, even now you don't know the value of a. Okay? You have no idea about a. Okay? Now, this equation 5, for applying we want to now apply the second boundary condition. But you know, second boundary condition is what? This is del y by del x when x equal to L is equal to 0. So before applying the second boundary condition, let us find what will be the value of del y by del x at x equal to x. For this, we will differentiate this equation 5 partially with respect to x. And you can see this partial derivative of y with respect to x will be what? This will be k times a cos kx times cosine of omega t plus pi. Okay? Now we will apply the second boundary condition. You know, in accordance with second boundary condition, this del y by del x will be equal to 0 when x is equal to L. So when you will take this x in RHS equal to L, definitely this del y by del x in LHS will be 0. So you can see our result becomes Ka times cosine of Kl times cosine of omega t plus phi equal to 0. Okay. Now you have seen earlier that this k is a constant which is given by omega over v. Okay. So instead of this k here and here, I have written omega over v. You can see, and this is equal to 0. Now you know this v is equal to a square root of y over rho, where y, you know, this is Young modulus of the material and rho is its density. Okay. Now you can see this equation a times omega over v times cosine of omega L over v is equal to 0. This condition may be satisfied if you take A is equal to 0. When you will take A equal to 0, the result will be 0. If you take A is not 0, but omega is 0, even then this result will be 0. This equation condition will be satisfied. But this is not the actual solution. This is a trivial solution because this A cannot be 0 at all time. Because if displacement A will be 0 at all time, then displacement of the particle will be 0 at all time, and it means there is no vibration of the rod. There will be no vibration. But since our rod is vibrating, so A can't be 0. Omega is frequency of vibration, and if it is 0, it means no vibration is taking place. So this solution that A is 0, omega is 0, these are called actually the trivial solution which are not possible. So you must take that neither A nor omega is 0. But if A and omega are not 0, definitely this cos function of omega L over B must be equal to 0. Okay? So we take that cos omega L over V is equal to 0. And you know, if cos theta is 0, what is the general value of theta? The general value of theta is written as n minus half into pi, where n is 1, 2, 3, 4 up to infinity. You may also take n plus half, but when you will take n plus half, then the least value of n you must take 0. It means then n will be 0, 1, 2, 3 and so on. But when you take n minus half, then you have to start the value of n from 1, not 0. You can't take n equal to 0 in this condition. So omega L over V is equal to this much. This is the general value. And so you can see here, since L and V are constant, so for different values of n, omega will have different value. So let us consider that when n is equal to n, then we will write this omega as omega n, not only omega. Okay? So omega n will be equal to n plus half times pi v over L. Okay? This is actually the angular frequency of the normal modes of vibration. Angular frequencies. And this result can also be written as n minus half times pi over L times root over y over rho, because this V is equal to this much. Okay? But if your aim is to find the regular frequency or the frequency which is measured in hertz, then you will write omega n equal to 2 pi nu n. Actually here nu n, you know, this is the regular frequency or the frequencies measured in hertz. So this above equation, which I am marking here, that gives actually the angular frequency of the normal modes for longitudinal vibration of a rod fixed at one end and free at the other. But this result will give the value of the frequencies of vibration of normal modes, those frequencies which will be measured in hertz. Okay. Now you can see this pi and this pi will cancel out in both sides, and therefore nu n is given as n minus 1 over 2 over 12 times a square root of y over rho. This is actually our final result for the frequencies of the normal modes of vibration of a rod which is clamped at one end and free at another end, and it executes longitudinal vibration. This equation will give actually all the frequencies present in the vibration of this rod. Okay. Taking the different value of n, we can obtain all those values. But before that, let us see what will be actually, you can say that this nu n is the frequency of nth mode of vibration. Now, first of all, we will see what will be the displacement of the particles of the rod in this nth mode. And for this, we will use this equation number 5. And in this equation now, this y will be written as yn because we are going to find the displacement of the particles of the rod in nth mode. A will be written as an, k will be written as kn, and omega will be written as omega n, and phi will be written as phi n. Okay. So the displacement of the particles in nth mode of vibration denoted by this symbol yn of x and t, this is given as an times sine knx. But you have seen what is the value of kn? Kn is omega n over v. Okay, omega n over v. And this omega n, you have seen that this omega n is equal to this much. So from here you can see when you will find omega n over v, what will be your result? This will be n minus 1 over 2 times pi over L. So this is actually the value of omega n over v, which will be written instead of kn. So at the place of kn, you can see I have actually written this much, n minus 1 over 2 times pi over L. This is at the place of kn times x and cosine of this much. Actually, this equation B will be used to find the shapes of the different mode of vibration. Okay. Equation A will be used to find the eigenfrequencies or the frequencies of vibration of normal modes of vibration, and this equation B will be used to determine the shapes of the different modes. Okay. Now let us see the different cases, different situations. First of all, we are thinking about what will be the lowest frequency present in this vibration of the rod. You know, if your aim is to find the lowest frequency, you have to take the least value of this n. And you know, least value of n is what? This is 1. When you will take n plus half, then least value will be actually 0. But when you take n minus half, the least value is 1. Okay? So when you will take n equal to 1, you will get the lowest frequency of vibration. And what will be that? This will be half over 2 times L times this much. This will be 1 over 4L times V. This is nu 1 and this nu 1 is 1 over 4L times V. But you know, instead of V, we may write this. So this is the lowest frequency of this longitudinal vibration of rod, which is clamped at one end and free at another end. Actually, this lowest frequency of vibration of the rod is called its fundamental frequency. Okay, this is called fundamental frequency or first harmonic. Okay, first harmonic. Now you can decide what will be the shape of this rod during this vibration. And for this we will find the displacement of the particles in this mode of vibration. And how we can find the displacement? By using this equation B, you can find the displacement. For this you have to take n equal to 1. So let us take n equal to 1 everywhere in this equation B. And you can see y1 of x comma t, this will be equal to a1 times sine pi x over 12 times cosine of omega 1 t plus pi 1. Okay. Now see this equation seriously, and you can easily say that when x is equal to 0, this y1 will be 0. Why? Because when you will take x equal to 0, this sine pi x over 2l, this will be equal to sine 0 when you take x equal to 0, and this is 0. So RHS will be completely 0. It means y is 0. So at x equal to 0, no particle at this position will get displaced. This will remain permanently at rest. Okay. So you can see I have shown here the graphical plot of y1 in against of x. Okay. And you can see that actually this y is 0 at x equal to 0. Okay. Y is 0 at x equal to 0. And you know where displacement is permanently 0 at all time, that is called node. So actually in this case, this point O is just a node. Okay. Now, you will see that this y1 is not equal to 0 except the point x equal to 0 in the region 0 less than x and less than L. It means between on the whole length of the rod, y is 0 only at the fixed end, not at any other point. And when you will talk about the other end, that is free end of the rod, which is lying at x equal to L, what will be y1? You can see when we take x equal to L, then this sine pi x over 2L, what will be this? This will be sine pi over 2L times x. X is now L. So this L and this L will cancel out, and this is sine pi by 2, and this is 1, which is the maximum value of sine pi x by 2L. Since in this condition, when you take x equal to L, sine pi x over 2L is maximum, and that's why you can say that this displacement y1 will be then maximum. Okay. Actually, and again you can see that there is no other value of x in the range between x equal to 0 and x equal to L, where this y1 will be 0. That's why the shape of this mode is like this, which I have shown in this figure. Okay. Actually, this figure represents the graph of this y1 in against of x. Okay. You must remember that this displacement y1 are longitudinal, not transverse. Mark it. Okay. Now, at this point x equal to 0, there is node, and at x equal to L, since displacement is maximum, so this point x equal to x L correspond to NT node. Okay. Now let us think about the next mode of vibration. You have seen that n is equal to 1, 2, 3 and so on. So just the successive higher mode of vibration will be n equal to 2. And when you will take n equal to 2, then you will get the frequency of vibration in this mode from this equation A, replacing n everywhere by 2. When you will take here 2, this will be 2 minus half, that will be 3 over 2. So that will be 3 over 4L times B. So you can see I have mentioned it here that in this condition the frequency nu2 is equal to 3 over 4L times this much. But you know that 1 over 4L times root over y over rho, this is equal to nu1. So this nu2 is equal to 3 nu1. This is 3 times of the fundamental frequency. Okay, 3 times of fundamental frequency. Now, again, in this case, what will be the particle displacement? For this, we will again substitute n equal to 2 in this equation number B. And after taking n equal to 2, you can easily see that y2 will be equal to a2 times sine of 3 pi x over 12 times cosine of omega 2t plus phi 2. Okay. Again, let us see this equation. You can notice that this y2 is 0 at x equal to 0. Okay. And it is again 0 at x equal to 2L by 3. Actually, at these 2 points where where y2 is 0, you know, these are called nodes. So in this case, there are 2 nodes. One is at x equal to 0 and another is at x equal to 2L by 3. Okay? And if you find the value of this y2 when x is equal to L, what will be that value? You can see when x is equal to L, then what will be this sine 3 pi x over 2L. Let us try to find its value when x is equal to L. So this will be sine 3 pi over 2L times L. Now this L and L will cancel out. So this is sine 3 pi by 2. And what is the value of sine 3 pi by 2? This is minus 1. So the absolute value of this sine will be maximum, but negative. So you can say that at x equal to L, this y2 is maximum but negative. Okay. And what will be the shape of this mode I have shown in this figure, you can see. Okay. Actually, when you will try to find the frequencies and the shape of the mode for higher mode of vibration, you can obtain the results in the similar manner. When you will try it, you will see that the frequencies which are present in this vibration of longitudinal vibration of rod are nu1, 3 nu1, 5 nu1, 7 nu1, 9 nu1, so on. What does it mean? It means actually in this vibration of rod, only the odd multiple of the fundamental frequency nu1 are present. Okay? Only the odd multiple of fundamental frequency. It means in this longitudinal vibration of a string, the even multiple of fundamental frequencies are not present, they are absent. That's why we simply say that all the overtones are not the harmonics of the fundamental frequency. This nu1 is fundamental frequency. 3 nu1 is actually the third harmonic. 5 nu1, this is fifth harmonic. But the second harmonic, fourth harmonic are absent. This is a very remarkable fact. When a rod is clamped at one end and it executes longitudinal vibration, its vibration does not contain the even multiple of fundamental frequency. Only the odd harmonics of the fundamental frequency nu1 are present in its vibration. All the even harmonics of frequencies, that is 2 nu1, 4 nu1, 6 nu1 are absent. Okay. So in this way you have seen how we can discuss the problem of finding the normal modes of vibration of a rod, particularly in the limit under the boundary condition when it is clamped at one of its ends. Okay. I think definitely this video has been interesting for you, and you have definitely enjoyed this video. Okay. Thank you very much.